All right, Chemistry 3101. This is Chapter 6, which deals with chemical reactivity and mechanisms. You're going to see that the first part of this chapter, the chemical reactivity section, is kind of a lot of general chemistry, and then the mechanism section will be all new content to you. So again, the first few sections should be mostly a review for you. Well, if we get started here, we're going to take a look at enthalpy, which I know you all learned about in general chemistry. Enthalpy is H, the variable H, and then change in enthalpy is delta H. And we know that delta H, or what we call Q, is the heat exchange between a reaction and its surroundings. And it's important that you understand that heat is the same as Q, and we know that definition is true. Heat is the same as Q at constant pressure. When you're at constant volume, heat is not equal to Q. That's change in energy is equal to Q at constant volume, but that's something else, okay? That's something you would have talked about in general chemistry. Well, if you think about this heat energy exchange between a reaction, right, whether we're putting in heat or whether heat is being evolved from a reaction, and then we look at that from the point of view of the surroundings. Well, when we looked at bonding in Chapter 1, we talked about bonding molecular orbitals, and we said that electrons will achieve a lower energy state when they occupy a bonding molecular orbital, right, when a bond is formed. Therefore, it stands to reason that when you want to break a bond, it's going to take energy, okay? So if you're wondering, what's this whole point about here? It's nothing more than if you want to break a bond between two elements, it's going to require energy. Energy is going to have to be put into that bond in order to break the bond. Okay. Well, there's a couple of ways that bonds can break. They can break either what's called homolytically or heterolytically. Now, homolytic bond cleavage is when the bond breaks to form two radicals. And I went over this arrow with you a couple times already in class, but when you have an arrow like this with one barb on it, that's called a fishhook arrow. That represents the movement of one electron, right? When we see a curved arrow with two barbs on it like this, this represents the flow of two electrons. And so if we have two single-headed arrows coming off of a bond, we're going to make two radicals. And this is what we call homolytic bond cleavage, right? They're each getting the same number of electrons. So we end up with a pair of radicals. In heterolytic bond cleavage, that's when we take both of the electrons and give them to one of the elements in that bond. And in that case, we end up with a cation and an anion. Well, when we're going to calculate enthalpy of a reaction in this chapter, and we're going to do it this morning, and I'll probably ask you a question on your quiz about this, the bond dissociation energies, or the delta H's for bond breakings, those correspond to homolytic bond cleavages, okay? Now, if you're wondering, what is a bond dissociation energy? If we look at table 6.1, and this isn't the entire table, this is just a few bonds that I isolated and put into this slide. If you look at bond dissociation energies, which we're going to look at in terms of kilojoules per mole, these represent the amount of energy that it takes to break that bond homolytically. So for example, if we just take a hydrogen bond, right, a bond between two hydrogen atoms, okay, not a hydrogen bond in terms of intermolecular forces, but if we look at the bond between two hydrogen atoms in the H2 molecule, we would have to put in 435 kilojoules of energy for every mole of H2 that we want to separate into hydrogen radicals. If you look at the hydrogen-oxygen bond in water, let's say, that takes even more energy. It takes 498 kilojoules per mole. And then if you look at carbon-carbon bonds, we have all kinds of different carbon-carbon bonds here. And again, if you look at table 6.1, you can see that there's even way more examples, right? Here we have a carbon-carbon bond in ethane. Here we have one in propane. Here we have one in isobutane. And you can see that they all have different amounts of energy that's required to break those bonds. And if you look at a bigger table, this comes from a different book, but this is, if that fit better on a slide, you see a table with a more exhaustive list of bond dissociation energies than the one that I showed on the previous slide. So you can see that we can go to a table like this, like table 6.1 in your textbook, and we can look up all kinds of bond dissociation energies. So again, when we are doing a reaction, think about all the chemical reactions that we've looked at in this class. We haven't looked at a lot of them in detail, but you've seen some, and you know that when you do a reaction, right, a chemical change, it involves breaking and forming bonds. Even if you go into high school science, and you discuss the difference between a chemical change and a physical change. Well, a chemical change involves breaking and forming bonds, and so there's going to be a total change in enthalpy associated with that reaction, and that change in enthalpy, that delta H, is referred to as the heat of reaction. Sometimes we'll call it delta H, and then I put Rxn here, which stands for reaction. Now, there's two types of changes in enthalpy that we're going to be concerned with: an exothermic reaction and an endothermic reaction. Well, what's an exothermic reaction? It says the energy released by the bonds that are formed is going to exceed the amount of energy that's required to break those bonds. So that means there's going to be energy released into the environment, into the surroundings. And in the case of an exothermic reaction, the products are more stable than reactants. Now, if you're thinking, what about a reaction coordinate diagram, Mr. Dion? I looked at those in general chemistry. We're going to look at examples of those on the next slide. Just give me a second here. What about an endothermic reaction? An endothermic reaction is where it's going to be a reaction that it takes more energy to break the bonds than you get that's released when the new bonds are formed in your products. And so in this case, the products are going to be less stable than the reactants, right? A picture is worth 1,000 words. And so let's take a look at some graphical representations of enthalpy. And these are just called reaction coordinate diagrams. You see here that on the y-axis of both of these, we have enthalpy. And then on the x-axis, we have reaction coordinate. That just means the progress of the reaction over time. So if we look at an exothermic reaction, so that's the first graph here, we have an exothermic reaction. We see that our products are actually more stable than our starting materials. And so the products are lower than energy. That energy that's, the energy difference between these is going to be released as heat into the environment. And the temperature of the environment or the surroundings is going to increase, right? Because again, heat is being released or formed by the reaction. And in that case, our delta H gets a sign of minus, so it becomes negative. So that's an exothermic reaction. The converse of all of what I just said is true for an endothermic reaction. We see that the products are actually higher in energy than the starting material. So that means we have to put heat into the system, don't we? Right? We have to put heat into it. And so the temperature of the surroundings is going to get consumed. That's another sassy way of saying, the temperature of the surroundings from the reaction, the surroundings are going to decrease, right? And in this case, our delta H is a positive value, and we have what's called an endothermic reaction. So you need to know the difference between an endothermic and an exothermic reaction. All right, there we go. Well, with all that in mind, let's see if we can use some data from table 6.1 in order to predict the sign and the magnitude of delta H for this reaction, and then we're going to identify whether the reaction is expected to be exothermic or endothermic. Well, if we take a look at what's going on in this reaction here we have a propane molecule, right? We know that this is CH3, right? There's a methyl group here, and there's a CH2 here, a methylene. But the only bond that's being broken in the propane is we have two bonds to hydrogen, right? And this carbon only has one bond to hydrogen. So the bond that's being broken is one of those carbon-hydrogen bonds. There's another bond that's being broken too, right? If I draw out the bromine molecule, right? Just draw the Lewis structure. Going back to general chemistry 1 and just drawing Lewis structures. You see there's no Br2 over here. And so we're also breaking this bond as well. So if we tally up the bonds that are broken, so if we tally up bonds broken, okay, we're going to have to put in energy, right? A positive amount of energy to break that bond. We're going to have to put in a positive amount of energy to break that bond, right? Energy in to break a bond, because we know that bonds are more stable than the radicals, right? If we have the free radicals. Okay, so how much energy does it take to break those bonds? Well, again, you'd have to go over to table 6.1, and I don't have the whole thing here, but if you go into table 6.1, I'm just hauling it up here quickly. Table 6.1, and you look at the carbon-hydrogen bond. So there's a whole section that deals with carbon-hydrogen bonds. I'm trying to find it right now. Here it is. Yeah, so you look at the carbon-hydrogen bond in the methylene of a propane molecule. It's the fourth entry. Again, if you look at table 6.1, it says bonds to hydrogen. You have a bond between H2, then you have a bond between a hydrogen and a methyl, then you have one in an ethyl. The next one is the methylene in a propyl, and that takes 300, oops, I'll use my black pen, 397, let me just label it here, 397 kilojoules per mole to break that bond. So that means it's going to require 397 kilojoules per mole. Then if you look up the bond dissociation energy of Br2, which is the third from the bottom on the table, you see that it takes 193 kilojoules per mole to break that bond. So we have 193 kilojoules per mole. If you tally that up, 397, so that means the total cost to break all the bonds in this reaction, or the bonds that are required to be broken in this reaction, is going to be 590 kilojoules per mole to break those bonds. We do the same thing for the bonds that are formed. If you look at the bond between this carbon and a bromine, it's found again in table 6.1. It's about 1, 2, 3, 4, 5, 6, 7, 8 up from the bottom. And you see that the amount of energy that's going to be released, right? Because now we're not talking about the bond being broken. The amount of energy that it would take to break the bond is going to be released when the bond is formed, okay? And so the amount of energy associated with the dissociation of this bond is 270, no, am I looking at the wrong one? No, hold on. Oh, I am looking at the wrong one. It's 285 kilojoules per mole. And then the amount of energy that's required to break an HBr bond, which is also in the table, is 368 kilojoules per mole. Now, there's nobody who couldn't do this. So now if I write out the bonds formed, okay, I have 285, okay, and 368. So these are both kilojoules per mole. Now, here's where it gets interesting. When the bonds are broken, we give them a positive sign, right? Because you have to put energy in. When the bonds are being formed, we give them a negative sign because energy is being released when you form a bond. So if I take a negative and I add another negative to it like that, I end up with negative 653 kilojoules per mole. And so the delta H of my reaction, right, the delta H naught for this reaction is going to be the sum of the enthalpies of the bonds broken plus the sum of the energies of the bonds formed. But since my bonds formed release energy, when I plug this in, I'm going to have 590 kilojoules per mole, and that should be 3 sig figs, plus negative 653 kilojoules per mole. And I get that the delta H of my reaction is going to be equal to negative 63 kilojoules per mole, like that. Okay, the main takeaway from this, everybody who's hearing the sound of my voice can add and subtract some numbers, and everybody knows what a positive and a negative is. Okay, the main thing is that you understand the reason this sign is negative is because heat is released, okay, when bonds are formed. Okay, give me a thumbs up if you follow me on that concept, and if you're like, yeah, if you gave me the table of values, yes, I could calculate a delta H for a reaction. Just want to be sure that you understand that when you break a bond, you've got to put energy in, so that's going to be a positive value. When bonds form, energy is going to be released, and so we have a negative value. All right, good. All right, let's see here. And there's some good practice problems in the book where it gets you accustomed to using table 6.1. And again, if I ask you to solve a problem like this, I'm going to have to give you the bond dissociation energies. You are not expected to remember any bond dissociation energies. Well, let's move on to entropy, right? It says here that an exothermic and an endothermic reaction, both of them can occur spontaneously. generally speaking, we have more exothermic reactions that are going to be spontaneous than an endothermic reaction. However, enthalpy is not the ultimate deciding factor as to whether a reaction is going to be spontaneous or not. It's actually entropy that is the deciding factor as to whether a reaction is going to occur or not. Now, if you're wondering, what the heck is entropy? I don't remember. Well, if you think of a messy bedroom, that's entropy, right? Just complete disorder, right? Disarray. It says here randomness or freedom, right? If you think about cleaning your kitchen, you know, when you're an adult and you have children, that's all your life is cleaning the kitchen. Well, I think about it, there's only a couple of ways for me to arrange the kitchen so that it's completely clean. But I can tell you, my friends, there is Avogadro's number of ways that it can be disorganized and that it can. So entropy is molecular disorder, randomness, or freedom. And in order for a process or a reaction, right, to be spontaneous, it has to have a positive entropy term. So that means it has to be the entropy of it has to be increasing for the reaction. Okay, and again, I know you're aware of what entropy is. Now, if you went back to General Chemistry 2, right, and looked at your thermodynamics chapter there, you did a lot of calculations in entropy. Well, I can simplify entropy even more for you in organic chemistry, because in Chemistry 3101, you're basically going to look at two scenarios where you're going to have to be able to evaluate the entropy of a reaction. Okay, the first one is when there's more moles of product than there are reactant, right? There's more ways that you can organize two individual molecules than you can one molecule. And so in this case, the delta S would be positive, right? There's an increase in disorder. Think about it. If you have one thing, it's going to be neater than if you have two things, right? If you have two things, well, you can organize them more than one way. And so the disorder is increasing. So that's pretty simple. And again, I don't like to use the word simple in chemistry class, but I think it's pretty intuitive. And the other one is when you have a cyclic compound and it becomes acyclic. In this case, also the entropy is decreasing. And I bet you if I ask my students why, you know, and I've done this in the past, you get some really simple answers, but they're always right. Okay, my students will say, well, come on, there's rotation around these bonds here, right? The conformations of a ring are much more constrained than when I have something linear. And so since the acyclic form can adopt more conformations, it's more disordered, and therefore the delta S is going to be positive. So these are the two dominant factors that you have to be concerned with respect to entropy. And you can see how I could ask a question about this really easily on a quiz. Something like this. It says, for each of the following reactions, predict the sign of delta S. In other words, will the delta S for the system be positive? Remember that when we see system, right, system is the same thing as your reaction. Okay? Well, if I look at A, could anybody tell me, would the delta S of my system be positive or negative in this case? And it's not a trick question. I don't know why I don't see the chat. Anyhow, yeah, all of my students are getting it correct. It's negative, right? Because I'm going from two molecules, right, to one molecule. So it's becoming more ordered. One molecule is one molecule. So you could write next to it becoming, we could say here becoming more ordered, and therefore it's a decrease in disorder. So therefore the delta system, or the delta S for the reaction, is going to be negative. The next one, we're going from from one molecule to two. So we're going from one to two things. And so the delta S for the system here is going to be positive, right? Oops, is going to be positive because disorder is increasing, right? There's more ways that we can organize two things than we can one thing. All right, and that's kind of a simple treatment, but it's going to suffice for Chemistry 3101. Now, you guys know that when I said the entropy is the ultimate deciding factor as to whether a reaction will be spontaneous or not, you know that the total entropy of the system plus surroundings is basically what we refer to as Gibbs free energy. And if you need a little refresher on that, I've got one right here. It says that the spontaneity of a reaction is going to depend on the total entropy, right? It depends on the entropy of the reaction, and it depends on the entropy of the surroundings, the environment around the reaction. Now, if you think about it, the delta S of a system, the delta S of a reaction is pretty easy to measure or do a quick estimation using entropy values from a table, right? If you go to the appendix of a general chemistry textbook, you can find some entropy values there. You're like, no problem, I can do that. You know, I remember how to do that. Well, what about the delta S of the surroundings? It's not that easy to measure the change in entropy of the environment around a reaction, but luckily we have a workaround for that. And I'm not going to go on about where this equation comes from, but we can define the change in entropy of the environment or the surroundings as being equal to the negative of the change in enthalpy of the system or reaction divided by temperature. So if we substitute this into, oops, I went to the wrong one, into here, we end up with the total entropy is going to be equal to the negative of delta H of the system over temperature plus the change in entropy of the system. So now we are going to be able to determine whether the reaction is spontaneous or not solely based off of the reaction. We don't have to think about the environment at all. And you're thinking, well, come on, I can go look up the delta H values or the H values in a table. I can look up the S values in the table. It's getting better all the time, right? That's what Paul McCartney said. So if I multiply this entire thing by negative T, right? If I multiply all this by negative T, you see that negative T is going to cancel out over here. And then we're going to end up with this equation right here. The negative T times the total entropy is equal to the delta H of the system minus T and delta S of the system. And you guys probably remember from general chemistry that this here, negative T multiplied by the total entropy is equal to Gibbs free energy, right? Delta G. Now, if you think about it, since when delta S was positive, that was a spontaneous reaction. Well, if we're multiplying delta S by negative T, that means that negative G means the reaction is going to be spontaneous, right? And conversely, we'll put here delta S, we'll say spontaneous. Therefore, we'll say negative T times delta S is going to be equal to negative delta G, which is also going to be spontaneous, okay? And then, of course, if your delta S is negative, you have a negative times a negative, which gives you a positive. And so when delta G is positive, that's going to be a non-spontaneous process. Again, this is just a review. This would be General Chemistry 2, the thermodynamics section of General Chemistry 2. And so if we really look at this equation, right, closely, what do we see? We see that the spontaneity of the reaction is determined by the change in enthalpy of the system, which is nothing more than the change in entropy of the surroundings, right? And we looked at that already. Subtract T multiplied by delta S, and that's the change in entropy of the system. So there we have the formula for Gibbs free energy, which you have to be fully aware of. Okay, now if we look at delta G, you probably remember the terms, right? You guys all remember exothermic and endothermic. Students always remember those. You probably remember exergonic and endergonic, right? It says that when the delta G is negative, right? That's a spontaneous process. I just explained why that's called an exergonic reaction. If we look at a different reaction coordinate diagram this time, right? Reaction coordinate is still here on the x-axis, but instead of enthalpy, now we're talking about free energy, delta G, Gibbs free energy. We see that when the products have a lower free energy than the reactants, we call this an exergonic process, right? Now, if you were to just put, some values on here, you say this is 50 and say this is 100, something like that. Well, if delta G is defined as the sum of the Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. For example, here you would have 50 minus 100, which would give you a negative number, right? So this is a spontaneous process, okay, when the products are at lower energy. If you look at an endergonic process, if we did the same treatment, I'm not going to write out the formula this time, but you see that when the products have a higher free energy, we end up with a non-spontaneous process. So again, you got to know the difference between exergonic and endergonic when you're taking Organic Chemistry 1. Got to know the difference between those. Give me a thumbs up if you just understand. I know what an endergonic process is. I know what an exergonic process is. Cha. All right, good. Okay, great. Again, I seem to be having some kind of problem with my chat here. I can see what you guys are doing, but I just have to click on something for some strange reason. Like, yeah, okay. Anyhow, whatever. Let's move on. Here's something that's near and dear to your heart if you took General Chemistry 2. And I know a lot of you took this class last semester. You would have done an entire chapter about equilibria. Then you would have looked at acids and bases, which treats equilibria from the point of view of acids and bases. Then you would have done things like KSP. Remember that? Okay. Well, those are all equilibrium processes, and those are important in this class as well. So if we think about an exergonic process, right, a spontaneous process, okay, you're like, good, I ran all the numbers, I calculated my delta H, my delta S, my negative delta, you know, I did all the calculations, and my delta G is negative. Is every single molecule of A and B of your reactants going to be converted into products in this reaction if your delta G is negative? The answer is no. Okay. The answer is it really depends. Okay. But generally speaking, the answer is no, because you're going to reach an equilibrium, right? You guys remember big K, the equilibrium constant? Well, it says here, in a spontaneous process, okay, in an exergonic reaction, we're going to have more products than reactants, but it doesn't necessarily mean that every molecule is going to be converted into products. Now, why the hell would that be? Well, we're going to see that in a second, but you see that the greater the magnitude of that negative delta G, all that means is that you've got more products, okay? The bigger the negative, or the more negative the delta G is, the more favorable it's going to be in terms of the products that are being formed. So my next question that I want to address is, why wouldn't everything just be converted to products if it's a spontaneous process? The reason why, okay, is because as the concentrations of A and B drop, right? You start here at the beginning of the reaction. All you have is A and B, but that drops over time, and you're forming more and more C and D over time. And then the collisions that occur between C and D are going to become more frequent. And then eventually you're going to reach a minimum value of delta G, which is where equilibrium occurs. And that's when the rate of the forward and the reverse reactions are equal. If we look at this from the point of view of a couple of formulas that you would have learned along the way, everybody who's hearing the sound of my voice definitely used this formula probably more than 100 times in General Chemistry 2, where you calculated a K equilibrium, which is equal to the product of the concentration of the products divided by the product of the concentration of the reactants. But how is the equilibrium constant related to delta G? Well, delta G is equal to negative R times temperature times the ln, or the natural logarithm, of the K equilibrium. Well, if I have more products than I do reactants, right, I'm going to have a bigger numerator than the denominator. And in that case, the K of the equilibrium is going to be greater than 1, right? If it's mostly products. Okay? Well, take your calculator, and if you don't have one, I'll do it for you. If you take the ln of a number that's greater than 1, so let's say you take the number 2 and you take the natural logarithm of it, you get a positive number. So that means that when K is greater than 1, when it's mostly products, you have this ln of the K is a positive number, and it's multiplied by a negative. What do you get when you multiply a positive and a negative? You get a negative delta G. Therefore, it's going to be mostly products, right? I'm just trying to connect the dots between negative delta G and mostly products. What if the opposite is true, right? What if it's mostly reactants, okay? In that case, your K equilibrium is going to be less than 1. If you take 0.5, a half, and take the natural logarithm of it, you get a negative number. What happens when you take a negative and you multiply it by a negative? Then you get a positive. That's going to be a non-spontaneous process, and you're going to have mostly reactants in that case, okay? So keep in mind that all of these terms, K equilibrium, delta G, delta H, delta S, these are thermodynamic terms. If you go back to your general chemistry notes and look at the thermodynamics chapter, you're going to see all of these terms come up in those chapters. But they have nothing to do with how fast the product or the reaction occurs. If you think about the reaction of diamonds to dust, okay? So if we go from diamond, where all the carbons are sp3 hybridized, to graphite, where where all the carbons are sp2 hybridized. We go from sp3 to sp2. That's a spontaneous process, literally. The conversion of a diamond ring into worthless or almost worthless graphite is a spontaneous process, right? Thermodynamically, the delta G is negative. However, the process takes so long, it takes millions or however many, millions of years, that it is something that we don't even have to consider, right? We don't even consider the rate of reaction when we're considering diamonds being converted to dust. So you see that kinetics and thermodynamics are two very different subjects, right? Again, this is just rehashing what I just said on the last slide. If your K equilibrium is greater than 1, less than 1, delta G is negative or positive, respectively. In order for a reaction to be useful, and there's a little slide in our book. I have it on the next one here. It says, in order for a reaction, this is where I'm talking right here. In order for a reaction to be useful, the delta G's got to be negative, and a little bit of difference in free energy has a huge, giant impact on the ratio of reactants to products. I'm going to skip the laws of thermodynamics and skip to this slide right here. This is one of these slides I'm probably not going to ask you a question directly about it, but I just want you to take a moment. It's like a beautiful piece of artwork. You go to the Louvre or something, you look at, the Mona Lisa, or a beautiful piece of artwork. And I just want you to admire the table and I know it's not a beautiful piece of artwork to most people, but just look at how small differences in delta G have a huge effect on the amount of products, right? If you go from 0 to -6 and -11, right? If you go just by changes of about 6 kilojoules per mole, you can go from, 50 to 90%, right? By only having a change of 6 kilojoules per mole. It's not that much, okay? And the opposite is also true, right? If you go in the opposite direction, you end up with basically nothing when you have a positive delta G, okay? Anyhow, again, I don't think I'll ask you anything about this directly, like, if you have -11 delta G, do you have a 99% yield of your products? Well, probably not. But yeah, anyhow, just something to think about. Anyhow, do you guys remember the laws of thermodynamics? Anyhow, this is a very shorthand version of the laws of thermodynamics, but you probably remember these things, right? Energy can't be created or destroyed. Entropy always increases in a reaction, and when you have a perfect crystal at absolute zero. So just kind of a refresher of the laws of thermodynamics for you if you need to take a look at those. But look, you're in chemistry in a 3000 level course. You should be aware of the 3 laws of thermodynamics in a 3000 level chemistry class. Anyhow, there we go. When it says DG, I don't know why that didn't come. This is supposed to say delta G. Anyhow, font, something to do with font. All right, let's take a look at some cases here. This is question 6.6. These questions, you could have been asked these in chemistry 1411 at UCCS. Every single one of these questions from question 6.6. So this is really a review. It just says, in each case, use the data to determine whether the reaction is going to favor the reactants or products. I'm going to ask my students about A, is this going to favor reactants or products? The first one, if delta G is positive, 1.52 kilojoules per mole. Yeah, thanks, Sarah. Absolutely, it's going to favor the reactants in A. Right, this is going to be a non-spontaneous reaction. Okay, it's going to favor reactants since delta G is positive. Okay, let's look at B. It says you have a K equilibrium of 0.5. Look, you can use delta G is equal to negative RT ln of K equilibrium. If you take the K equilibrium of 0.5, the ln of 0.5. So if you take 0.5 and take the natural logarithm, remember, whenever you take the natural logarithm of something that's less than 1, you get a negative number. So we have a negative times a negative over here. So that means your delta G is going to be a positive number. When delta G is positive, it's non-spontaneous, as we just said, and so it's going to favor, thinking of too many things here, favor reactants in this case. All right, let's move on and look at something maybe a little more complex. It says in C, you have a reaction carried 298 Kelvin, so that's 25 degrees Celsius. You've got a delta H of positive 33 kilojoules per mole, and you have a delta S of positive 150 joules per mole Kelvin. Well, in this case, you can just use the formula. In C, you can use the formula that delta G is equal to delta H minus T times delta S. The only problem here is that our units don't work together, do they? Here we have kilojoules and here we have joules. So since delta G is normally evaluated in terms of kilojoules per mole, we're going to convert the entropy factor. We'll convert this to joules per, or kilojoules per mole Kelvin. And you guys probably know that there's 1,000 joules in 1 kilojoule. So this is going to be the same thing as 0.150 kilojoules per mole K, like that. So let's plug in some numbers so we get that our delta G is going to be equal to 33 kilojoules per mole. Subtract 298 Kelvin multiplied by 0.150 kilojoules per mole Kelvin, like that. You see that Kelvin cancels out, and I'm just going to do some quick math here. So we get 33 kilojoules per mole, subtract, so 298 times 0.15, so that's 44.7 kilojoules per mole, and we get that our delta G is going to be equal to 33 subtract 44.7, and we're going to end up at negative 11.7. Since we don't have a decimal place here, technically it should just be negative 12 kilojoules per mole. And so this is going to be a spontaneous process, right? So it's going to favor products. Products favored. Give me a thumbs up if you know how to use the delta G reaction or delta G equation. Delta G is equal to delta H minus T delta S. Cha? Hope so. Okay. I know you do because you all passed general chemistry too. Okay, I know that for sure. And then let's try D and E. These are the most classic scenarios that you can end up with in general chemistry 2, right? General chemistry 2 instructors love to beat the hell out of these questions here. It says you get an exothermic reaction, so that means your delta H is negative with a positive value for delta S of your system, so that means that delta S is positive. So if delta G is equal to delta H minus T delta S, we have a negative number here. Subtract a positive number for your temperature times a positive number for your delta S. So that means that delta G is equal to a negative, subtract a positive number. So if you have a negative number and you're subtracting a positive number from it, that means that delta G is always negative. No exceptions, right? Think about it. If you take negative 2 and you subtract 2, what do you get? Negative 4. So delta G is always going to be negative, and therefore products are always going to be favored. All right. In the interest of time, I'm going to skip E. Make sure you take a look at it, and we're going to move on to section 6.5, which deals with kinetics. Right? Kinetics is the rate. Right? How long is this reaction going to take? How long will this lab take? Can I leave early? Right? It's all about speed here. So recall that delta G just tells us whether reactants or products are going to be favored. Okay, exergonic, endergonic, you got to know the difference between those. It doesn't tell you, again, anything about how fast it's going to happen. Right? You set up a reaction. You're a researcher. It's a reaction nobody's ever done before. You run all the numbers. You calculate delta G. The delta G is negative. You're super excited. You do the reaction or you start it, and then it takes a month. Well, that's not very useful, generally speaking, okay? So some spontaneous processes or some reactions that have a negative delta G are really quick, like an explosion, right? Great example. You produce a lot of gas. There's some really good reading material in this chapter. It talks about Alfred Nobel and how he discovered, different explosives and how he mixed, nitro with diatomaceous earth, and then he ended up making dynamite and stuff like that. Anyhow, there's some interesting food for thought in there. But it says some spontaneous processes, and this is the one I was referring to, that where you take a carbon that's a diamond and you convert it into graphite, it takes millions of years, but it is spontaneous, okay? But since you probably won't be around in a million years, don't worry about it, you know, don't sell your diamonds yet. Okay, the reaction rate is a function of the number of molecular collisions. This is effective. Think about how fast a reaction is going to occur, right? Go back to your general chemistry too. Why does a reaction occur? It occurs because molecules collide with one another, right? We've got to have collisions, but not only do we have to have collisions, they have to be effective collisions. What's going to affect whether a collision occurs, number one, and whether it's effective or not? All of these factors here come into play. The concentration of the reactants, okay? If you go back to your rate laws from general chemistry 2, you learn things like this. The rate is equal to K times A, let's say for a first order reaction, okay? This is just an example off the top of my head. But what do we know? If the concentration of A increases, this is a direct relationship, therefore the rate of the reaction is going to increase. Also, what about activation energy? Things like temperature, geometry, and sterics, or the presence of a catalyst. Well, all three of these here, okay, activation, energy, temperature, geometry, and sterics, these are all factored into K through the Arrhenius equation. K is equal to A times E to the power of negative EA over RT, right? You have the activation energy, number 2. You have the temperature, number 3. You have the geometry and sterics, which is, that's A, it's in the steric factor here. Then the presence of a catalyst can also affect the activation energy. I don't even think that the Arrhenius equation shows up in our textbook, but if you wondered, like, where are those, you know, in terms of the calculations of reaction rate, those are factored into the rate constant, okay? Again, I'm just reviewing general chemistry 2 with you. All right. Well, if we think about a rate law, and this is just a simple rate law here, we have rate is equal to K times the concentration of our reactants. It's to the power of 1 here, and so this is a first order reaction, is at least what it looks like. Again, as the concentration of the reactants increases, the rate is going to increase. All right, but the degree to which the change in the concentration of the reactant is going to affect the rate is known as reaction order. Now, I know that you all learned how to determine reaction order because it has to be determined experimentally. You probably would have learned the method of initial rates in general chemistry 2, where you compare two different reactions that have different reaction rates, and then you vary the concentrations, and that's how you determine these exponents here. We're not going to go over that at all, okay? You should know, though, if you have a first order reaction like this one, what's going to happen if I increase the concentration of A by a factor of 2? Well, it's going to cause the rate to go up by a factor of 2, okay? Because it's first order, right? The exponent there is a 1. If you have a second order reaction, if you were to double the concentration of A and keep this the same, it's going to double the rate. If you were to double the concentration of B and leave this the same, then it's going to double the rate. What if you had a third order reaction like this one here? And we could go on about this all day long. If you double the rate of A, then you're going to have 2 to the power of 2, which is equal to 4. So then the rate is going to quadruple. Right? Again, these are general chemistry 2 concepts. Give me a thumbs up if you remember these even a little bit, right? You remember that the exponents have to be determined experimentally, and you should be able to evaluate what the effect in the change of concentration of one of the reactions would be on the rate of reaction. You should remember that generally speaking, if you have a large K, right, a big rate constant, it's going to be a fast reaction. If you've got a little tiny K, it's going to be a slow reaction, right? Again, if you took general chemistry 2 at UCCS, which I know a lot of you have, that would be chemistry 1411. If you have your notes or your binders or your textbook, if there's any concepts you're like, I think I get it, but I'm not 100% sure. Well, I don't promise, but I bet that if you go back and just looked at your note for like a second, you'd be like, oh, yeah, I remember that. Because a lot of you wrote a final exam on the content that I'm talking about, you know, not that long ago, back in December. So that's not that long ago. I mean, we could sit here and talk about these factors that affect the rate constant all day. I'm going to go over these pretty quickly. The reason why is not because I want to rush over them. They're not important or anything like that. It's because I find that the factors that affect rate constant are one of the few concepts in chemistry. I shouldn't say few, but it's one of the concepts in chemistry that it's a beautiful thing, and that so many students that I have taught over the years find this intuitive. You know, you explain it to them and like it makes total sense. So for example, if we look at an activation energy, right? That's just the energy barrier between reactants and products, right? It's the hump that you got to get over right here, the activation energy. It's the amount of energy that's required for the reactants to overcome. It's that threshold energy that they have to obtain in order to get to the downhill slope to get to the products in the case of this exergonic reaction here. So the activation energy, I mean, how fast the reaction is going to occur is going to, of course, be related to the activation energy, right? If the activation energy increases, well, you're going to have less molecules that are going to have that threshold, that minimum amount of energy required to overcome that threshold, right? To get to the downward slope to the products. What if you lower the activation energy? Well, of course, that's going to increase the rate of reaction because you're going to have more molecules that are able to overcome that threshold, right? Activation energy. If you look at it in terms of the number of molecules at a certain temperature, so this is at a certain temperature, we have the Boltzmann distribution, which shows the average energy or the average kinetic energy of molecules here. Now the average energy, let's say, is somewhere around here. We'll say this is energy average or something like that. But if the activation energy is right here, then that means that at this temperature, we're only going to have that amount of molecules that are in this shaded area here that are going to have the energy necessary to overcome that energy barrier. What would happen if we lowered the activation energy, right? If you were to lower the activation energy, let's say, I didn't mean to use that, right? If you change the activation energy to a lower activation energy, what's going to happen? You're going to have a greater number of molecules that have the necessary energy to overcome that energy barrier between the reactants and products, okay? Here's it shown in a reaction coordinate diagram, right? And I'm really rehashing the same thing in 3 different slides, aren't I? I'm really repeating myself here, but you know what? I'm 43. I've earned the right to repeat myself like an old man and tell the same stories over and over. So the lower the activation energy, the faster the rate. Give me a thumbs up if you follow me on that. You just lower that activation energy. I know that some of you are already trying to mentally tie this to a catalyst. You're like, I think this is related to a catalyst, isn't it, Mr. Dion? Kind of, yeah. Catalysts are a way to lower activation energy, but the difference between just simply lowering activation energy and a catalyst is that a catalyst is going to have a different pathway. So we'll look at that in a little bit, okay? What about temperature, right? I know you all saw this figure in General Chemistry 1 probably when you talked about the Boltzmann distribution. You said at a higher temperature, the curve flattens, okay, but it broadens. Okay, when we look at the number of molecules versus their amount of kinetic energy. So if we have a higher temperature and we have this activation energy down here, you can simply see that at a higher temperature, I mean, you got more molecules that have enough energy to produce a reaction. There's a rule of thumb, and I know that students love rules of thumb. There is a rule of thumb in organic chemistry and in general chemistry too, that if you increase the temperature by 10 degrees Celsius, it will double the rate of reaction. I don't think that's going to come up on a quiz or anything, but just to throw that out there to you. Steric considerations, I'm not going to go over this a whole lot because it's going to be covered quite extensively in chapter 7, but hopefully you remember that when 2 molecules collide, it's not good enough that they just collide. It's not just wham, you know, hey, 2 molecules met on the street and you got a beautiful reaction. No, it doesn't matter how fast, how hard those molecules are colliding unless they collide with the correct orientation. So that's a steric factor. And again, we're going to talk about that a lot in chapter 7. I mean a lot. So worry about that then. And then a catalyst. Again, I know that a catalyst lowers activation energy is what it looks like here, but it's not simply lowering activation energy. It provides an alternate pathway. Okay, so it does lower the activation energy, but it also, before when we just talked about changing activation energy, we didn't see all these humps and bumps here in the new pathway. And we're going to look at several reactions in this class that involve catalysis, okay, involve the use of a catalyst. Really interesting reactions. We don't study their mechanisms in gross and dirty detail because some of them can be kind of complex, but we will look at a couple of them, so something to look forward to there. Let's move on to section 6.6. This just deals with reading these energy diagrams, right? Looking at a reaction coordinate energy diagram and being able to understand what the heck is going on, right? Remember, I can't stress this enough. If you're unsure about why kinetics, the rate, and thermodynamics, the stability of products, are two different subjects, make sure you understand that before you step into the quiz. Make sure you understand that before you step into organic chemistry too. If you're the kind of person that wants to write an MCAT or a DET, you need to understand there's a big difference between kinetics and thermodynamics, right? Kinetics, rate of reaction, activation energy, right? It's getting over that barrier, right? The smaller the barrier is, the faster the reaction. The greater the barrier, the slower the reaction. Thermodynamics, on the other hand, deals with equilibrium. How stable are the products, right, compared to the reactants? Okay. If you compare these two reactions that you see in this reaction coordinate diagram here, you have two pathways for the reactants A and B. They can either react on the blue line and give you C and D, or they can react on this red line, this red pathway, and give you E and F. Well, if you look at the pathway to products C and D, you notice two things about it. First of all, if we look at the activation energies for both of these, you'll notice that the activation energy for the blue pathway is smaller than the activation energy for the red pathway. And so the products C and D are going to form faster, aren't they? Yeah, why? Because the activation energy is lower. Also, the products of C and D are more stable, aren't they, right? Why? Because they're lower in potential energy. And so, therefore, we could say that the formation of C and D is not only kinetically favored, but it's also thermodynamically favored. Okay? It's a double whammy, both kinetically and thermodynamically favored. Now, I don't have the ACS final memorized, but I do remember it enough, and I'm only allowed to see it on exam day. You know, I go get them from the department, and then they have to take them back and they lock them up or whatever. But I remember that this is one of the first questions on an ACS final that I gave to my students a couple years ago, where it had this exact diagram and it just said, you know, C and D, what are they? Are they kinetic and thermodynamic or whatever? You know, anyhow, it's kind of an interesting question. If you look at this diagram here, right, if we interpret this one here, you can clearly see that the pathway to E and F is kinetically favored because the activation energy is smaller, but you can see that the products C and D are thermodynamically favored. Why? Because they're more stable. They're lower in kinetic energy. Now, most of the time, and this is something that I actually highlighted in our textbook in my electronic version, most of the time, the reactions that we're going to look at are both going to be kinetically and thermodynamically favored most of the time, but sometimes they are in competition. Okay, we do look at some examples where they're going to be in competition. And so in that case, we're going to have to decide what are we going to do in order to maximize the amount of products, whether we want E or F, E and F, or C and D. All right, what else? You need to know the difference between transition states and intermediates. If you look at a reaction coordinate for a reaction that has more than one step in it, so you see we have kind of like it goes step one here, then you form an intermediate, then you go through another step, you form another intermediate, then you do another step, right? Well, what are the significances of these maxima and minima in this reaction coordinate diagram? The maxima, these are called transition states, and the minima, or the valleys, these are called intermediates. And there's a difference between transition states and intermediates. In our book, he talks about how a transition state is likened to a person jumping up on a desk and then somebody taking a picture of them. They said if they take a picture of it, if your friend takes a picture of you trying to jump up on a desk and catches the picture of you while you're suspended in midair, that's a really high energy. You're in a high energy position there, and that is a very short-lived position, right? You can look at it, but it was very short-lived. And that is akin to a transition state. It's a high energy state that the reaction passes through. You can see this reaction here. So this is what we call methyl bromide. This is methyl chloride. This is the reaction where we take chloride, it reacts with methyl bromide to make methyl chloride. In a bromide ion, the transition state is where bonds are simultaneously being broken and formed. So bonds are being broken and formed at the same time. Transition states are fleeting. They're very quick. It's like the person being suspended in air, right? You can take a picture of it, you can think about it, but it's very short-lived. You cannot isolate a transition state. Okay? Again, they represent where bonds are being broken and formed. You need to know that that's what a transition state is. If we look at an intermediate, which again is the minima or the valleys in these reaction coordinate diagrams, the intermediates are observable, okay? They're actually going to exist for a period of time before moving on to another reaction, whether they produce another intermediate or a product. We are going to look at, I was going to say gazillions, I don't know. We're going to look at a lot of intermediates over the course of this, of Chemistry 3101, and probably even more intermediates in Chemistry 3111. A lot of intermediates. All right. Next subject is going to be the Hammond Postulate, and then we're going to move on to section 6.7, which is really where the rubber meets the road, and that's when we're going to start talking about new concepts in this chapter. So the last thing is the Hammond Postulate. Don't be intimidated by the name, oh, postulate. Ooh, sounds complicated. No, it's not meant to be complicated at all. All the Hammond Postulate is just looking at the maximum, looking at the transition state, and deciding or concluding whether the transition state more closely resembles the reactants or the products. Okay, so if you have an exergonic reaction like this one here, right? You see the products are more stable than the reactants. Well, if you look at the transition state here, you see that it's closer in energy to the reactants. That means that at the transition state, at this point here, the intermediate that's there, okay, the transition state, I shouldn't say intermediate, I should say the transition state more closely resembles methyl bromide than it does methyl chloride, okay? Now, if you're not 100% sure what I'm getting at there, okay, I have it cleared up here maybe. If you have an exothermic reaction, okay, so this is an exothermic reaction right here. If you look at the transition state, it's going to more closely resemble the structure of the reactants. That means the bonds are not going to be mostly broken. They're going to be mostly formed, right? Because here the bonds are mostly formed, or it's going to mostly resemble the reactants. Conversely, in an exothermic reaction, the transition state is going to more closely resemble the products. Nothing more than that. It's the kind of thing that we could go into a lot more detail about, but our book really only asks you to know these two things. Really, if I could summarize this Hammond Postulate, all you need to know is that in exothermic reaction, the transition state is going to look more like the reactants. Why? Because they're closer. And in an exothermic reaction, the transition state is going to look more like the products. Why? Because they're closer in energy. That's it. That's the take-home message. And if you're like, well, that's kind of simple, that's what it's supposed to be. It's not supposed to be any more difficult treatment than that. And if you're wondering, like, what kind of question would you ask me about that? Well, besides the content that's on this slide, the Hammond Postulate is going to come up more in chapters 7 and 8. We'll look at it even more then. All right, take a deep breath. There we go. And let's move on to section 6.7. I mean, most of everything that we've looked at up to now, maybe 6.6 is a little new, the transition state. But I know that in general chemistry, I talk about transition states with my students a little bit. We definitely discussed those a little bit. Hammond Postulate. But pretty much, I'd say probably 90% of what we've looked at thus far should be a review. I'd be a fool to think, oh, do you remember every single thing that you ever learned in general chemistry too? No. However, we do expect you to have a pretty good understanding of the concepts that you learned in that class. That's why it's required to take this class. Okay, now we're going to get into things that are totally new to you, okay? Unless you've studied organic chemistry, maybe somewhere else, you've probably never heard of a nucleophile and an electrophile. But you might have heard of an audiophile, right? If you say, oh, this person's a real audiophile, what does that mean? It's somebody who's into, fancy stereos and all the hi-fi and the best speakers and the best headphones and the best receivers and all those kinds of things. It's somebody that loves something, right? So a nucleophile is something that loves a nucleus. What's the charge on a nucleus? Positive. And an electrophile is something that loves an electron, right? What's the charge of an electron? Negative. So ionic or polar reactions, which are most of what we're going to cover in Chemistry 3101, we will look at exceptions. Exceptions would be what are called pericyclic reactions or radical reactions. That's for another day. Don't worry about that at all. So ionic or polar reactions, and this is where the class is going to get interesting, because now we're going to start talking about reactions a lot. When does a reaction occur? An ionic or polar reaction occurs when one reactant has an area of high electron density and the other one's got an area of low electron density. What if you look at these two molecules down here? You got methyl chloride and methyl lithium, right? Two very different molecules. If you look at the dipole between carbon and chlorine, well, chlorine is more electronegative than a carbon, right? So that means it's going to pull more of the electron density towards itself, right? That's what electronegativity is. It's the ability of an atom to pull electron density towards itself in a covalent bond. So that means our carbon is going to have a positive charge, right? We could even say the carbon is delta plus. If you look at methyl lithium, it's a pretty similar molecule, but look at this. Lithium is much less electronegative than carbon, and so carbon is going to pull more of the electron density towards itself. And so here in methyl lithium, you see the carbon is delta negative. Wow, those are very different, right? So in methyl chloride, the carbon is electron deficient, right? It's partially positive. We say it's electrophilic. Why would it be electrophilic? Because electrophilic means loving electrons, right? Desiring electrons. If you're positive, you're like, bring me some electrons. I want to balance out this partial positive charge. Why would this carbon be called nucleophilic? Because it's electron rich. It's looking for a nucleus, right? A nucleus is positively charged. Opposites attract, right? So if the carbon is positive, it's electrophilic because it's going to seek electrons. If the carbon is partially negative, it's going to be nucleophilic because it's going to seek a nucleus. You need to be able to look at molecules like these and decide, is this carbon nucleophilic or is this carbon electrophilic? Those are the kind of things you need to look for. If you're wondering, are there some, quick and dirty rules I could use for that? Well, a nucleophile, again, which is a nucleus lover, something that's seeking a nucleus, right? A nucleus is positively charged. A nucleophile is going to be able to donate a pair of electrons. What's something that's an electron donor? A Lewis base, okay? So if you see a Lewis base, you're going to know that it's a nucleophile. Also, if you have something that's more polarizable, it's going to be a stronger nucleophile. Now, if you don't remember what polarizable is, I'll get to that in a second. But if you look at all four of these down here, all four of these could be nucleophiles. Why is this nucleophilic? Because the carbon is delta negative. It's pulling most of the electron density towards itself. So it's like looking for a nucleus. Look at ethoxide. I mean, come on, good gravy. It's got a negative charge right on it. If we look at ethanol, you might think, well, why would ethanol be a nucleus lover? Well, because you have unpaired electrons that are not being shared in a bond. And so those are going to have the ability to be attracted to a nucleus, which is positive. And then over here in an alkene, we have a pi bond. We have two electrons in a pi bond. Pi bond is weaker than a sigma bond. And so put in the right environment, those pi electrons, those two electrons in that double bond can be attracted to a nucleus, okay? If you don't remember what polarizable is, it might be something that you might want to look up, the definition. But polarizability just means the ability of an electron cloud to distort itself, okay? So the bigger the electron cloud is, the greater ability it has to distort. So if you were to compare the how strong a nucleophile is, if you were to compare ethoxide to a sulfide like this, or a thiolate, this is going to be a stronger nucleophile, and the reason than than ethoxide if we just compare the two. Because the sulfur atom is bigger, right? If you go down group 6A, right, you go from oxygen to sulfur. Sulfur is a bigger atom, so therefore its electron cloud can become more distorted, and therefore it's going to be a stronger nucleophile. I'll go over that concept with you again before the course is over, but there we go. What about an electrophile, an electron lover, something that's seeking electrons? Well, we said, or we say that an electrophile is going to be a Lewis acid, right? What's a Lewis acid? A Lewis acid is an electron acceptor. Okay, you can either have a carbon that's partially positive, which is going to be an electrophile, right? Why? Because it's partially positive and electrons are negative, so they're going to be attracted to one another. Or if you have a carbocation, that's going to be a great electron acceptor, right? It's just looking for electrons to bind to this carbon to fill up the empty p orbital. And so carbocations are also electrophilic. Okay, so you've got to be able to recognize nucleophiles and electrophiles. Here is a summary of some common nucleophiles and nucleophilic centers and electrophilic centers. So what are the things that you look for in a nucleus lover? Remember, nuclei are positively charged, so we're looking for things that have electrons, that are ready to give them away, that are ready to share, okay, that are just looking for a nucleus. Well, if you have an inductive effect and if you have a dipole such that you have more electron density on one element than another, this carbon here would be nucleophilic. We went over that. What about a lone pair? I went over that, and I also went over a pi bond, why those could be considered nucleophilic. Again, in the right environment. If we're talking about electrophiles, those are electron lovers. They're going to be positive or partially positive. An example would be a carbocation is a great electrophile, or if you have a carbon atom that is partially positive, it's going to make a good electrophile. So if we were looking at this molecule over here, you know, if we're looking for nucleophiles, things that are nucleophilic, I'll try to color code it. The yellow will be nucleophilic, right? We know on this hydroxyl, there's some lone pairs, so that's going to be nucleophilic, right? The same thing, there's lone pairs on this nitrogen here, which will also render this nucleophilic. Okay, you could say the same thing here, right? We have a negative charge here, so this is going to be nucleophilic. What about electrophilic centers? Okay, carbons that are partially positive. Well, I'd say there's a couple of them here. This is going to be electrophilic because you have a dipole in this direction. Oxygen is delta negative compared to the carbon, which is going to be delta positive. Right, oxygen is the second most electronegative element in the whole periodic table. So there's definitely going to be a dipole in this direction, and there's going to be an even stronger dipole here because you could draw a resonance structure that shows a carbocation here. I'm not going to do it, but this is going to have a strong dipole going this way, and so this carbon is also electrophilic. Now, I went over that quickly for a good reason, right? There's a reason why I didn't say, hey, does anybody know which ones are, because you have to train your eye to recognize electrophilic centers and nucleophilic centers. And I promise if you work at it, you'll definitely be able to recognize electrophiles and nucleophiles when you see them. Well, section 6.8, I know we only have, half an hour left, deals with mechanisms and arrow pushing. Now, I already told you how when we use a curved arrow that has a double head, this represents the flow of 2 electrons, right? This represents the flow of 2 electrons. We looked at those in acid-base reactions, right? This one here shows a bond being formed between the base and a proton. This curved arrow here shows a bond being broken to form this conjugate base over here. Now, David Klein has developed a method for students to learn arrow pushing or curved arrows mechanisms in ionic or polar reactions, which is what we're going to be concerned with 95% of the time in our class. And he broke them down into 4 different ways that electrons move in these mechanisms. A nucleophilic attack, which we use Na, the loss of a leaving group, which we call an LLG, a proton transfer, PT, and a rearrangement. You need to be rock solid on these for your next quiz. Okay, so as you can imagine, we're going to spend a lot of time focusing on these during the next class. So I know we've only got 3 minutes left, so it's not a lot of time. I'm not going to go over this in detail. I just want to show you some of these concepts. Like, he breaks down the nucleophilic attack in a lot of detail, gives you some good examples. He explains what the loss of a leaving group is, what a proton transfer is, and what a rearrangement is. Okay? And what I want to do is, next class, I want to go over section 6.8 with you pretty quickly so that we can get into section 6.9, where we really hone our skills of recognizing loss of leaving group, rearrangement, nucleophilic attack, proton transfer, right? You've got to be very quick at not only recognizing those, but you've also got to be able to draw those. Now, there is one downfall, major downfall of the pandemic and doing quizzes using Respondus Lockdown Browser, and that I'm limited to doing quizzes on Canvas, and I'm unable to quiz you on Canvas and get you to draw curved arrows. But it is imperative that you learn how to draw the curved arrows. Simply recognizing them will not suffice, okay? Now, if you're thinking, well, it's a bullet, I can just dodge that and then I don't have to do it. I promise you that it's something you do have to master. And also, just think about next semester. It's looking like we're going to be face-to-face. So you're going to have to be able to draw curved arrows well, okay, proficiently. And you definitely have to do it this semester as well.